In part 2, I introduced the groups and their associated elements and mentioned the four principles, being the solubility product, acid-base reactions, redox reactions and buffers, as well as the common ion effect. In this presentation, I will be discussing sample preparation, the separation flowchart, and try to explain without detail some of the chemical reactions, all of which will be elaborated on in the future presentations within this series. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. As a miner, prospector, or hobbyist, you would collect your samples from the field, meaning it would be from the ground that you are working on or sampling. It would be either placer soils and gravel, or hard rock chips that you've broken off from a vein of some sort. Now these samples will need to be properly prepared. You will need to reduce each sample size by pulverizing and grinding until it is reduced to about minus 200 mesh. Each sample will need to be washed in cold distilled water and decanted to remove unwanted organic material such as tree needles, leaves, twigs, etc. The samples are then evaporated to dryness using low heat well below the boiling point. Then each sample is homogenized by thoroughly mixing each sample separately. Do not combine the sample into a single sample. Each sample should weigh about 1 kilogram and quartered. 1/4 of the samples are used for analysis. 1/4 set aside in the event of a mistake or error or other problem, and the last half to be stored for potential further study. Do not forget to label and record each sample. If you do not have a pulverizer or grinder, a hammer, and a steel plate, and a mortar and pestle will work just fine, although more labor intensive. The hardware that will be required to physically separate the groups and the associated elements is as follows. You will need 24 Pyrex test tubes with stoppers or caps, each having a volume of 30 milliliters. You will need 2 to 3 nickel or graphite crucibles, capable of containing up to 5 grams of material. You'll need a hot plate, preferably with a magnetic stirrer. You'll need some Pyrex spatula stirring rods. Now I use Pyrex spatulas because they have these little tiny shovels on the ends of them. It saves from buying special spatulas for the job. You'll need a centrifuge or filter funnels and filters. You'll need a muffle furnace or a torch, but a Bunsen burner will work just as well. A few Pyrex beakers of various sizes, usually up to 1 liter. A few volumetric flasks and some graduated cylinders of varying sizes up to 1 liter. You'll need some pipettes, a good lab scale, a pulverizer grinder, but a hammer and a steel plate with a mortar and pestle will do just fine. There are several reagents that will be required, all of which should be labeled as ACS. The acronym stands for American Chemical Association. It signifies that the reagents are of the highest quality and are the purest of chemical with negligible to no contaminants present. All solutions should be of the highest concentration and strength, as it saves money as you will need to dilute these. The reagents are as follows. 1 liter, hydrochloric acid 37% fuming. 1 liter fuming nitric acid 98% fuming. 1 liter sulfuric acid 98% fuming. Liquid bromine used to make bromine water. Small cylinder of hydrogen sulfide gas with regulator and valve can be purchased from your local gas supplier. Ammonium chloride solid. Ammonium hydroxide solution 35%. Ammonium carbonate solid. Zirconium nitrate, solid. Distilled water, and of course litmus paper or pH meter. There is also one more table for now that needs to be found and downloaded. It is a copy of the relative strengths of the Bronsted-Lowry acids and bases. If you are not able to find and download free copies of these tables, feel free to contact me and I will send you a PDF copy containing these tables and more. They are a must-to-have going forward. This table is a summarization of the group separation schema. The group classifications are based on the formation of chlorides, sulfides, hydroxides, carbonates, and finally metallic ions left in solution. Chlorides are insoluble in cold hydrochloric acid. Adding hydrogen sulfide gas adds sulfur to the solution. The group 2 elements are insoluble in solutions as they form sulfide molecules. Adding hydroxide and additional chloride in the form of ammonium compounds to the solution allows the formation of the group 3 compounds, which are insoluble as hydroxides. The rest will be soluble in a chlorinated solution. Due to the lower Ksp values, which will be discussed in a future presentation later, the group 4 elements can be precipitated as sulfides with the addition of hydrogen sulfide gas. Adding ammonium carbonate results in the formation of the carbonate complexes which are insoluble. All others will remain as ions. This is evident when you refer to the solubility of common compounds and waters table that I suggested that you locate and download a free copy of in presentation 2. The classifications associated with the groups, being chlorides, sulfides, hydroxides, and carbonates, is based on the formation, that is, the precipitated products with the metallic ions in various pH conditions, being either acidic, basic, or neutral. They are also based on the Ksp value. This will be discussed in a later presentation within this series, but for now, let's just state that any Ksp value of a product that is less than another will be able to precipitate. Example would be copper sulfide, which has a Ksp value of 6.3 times 10 to the minus 36, whereas manganese sulfide has a Ksp value of only 2.5 times 10 to the minus 13. Since copper sulfide has the smaller Ksp value, it will precipitate. This table shows the relationship between the groups and the reagents used. The chlorides shown are insoluble in accordance with the solubility of compounds and water table. As the gas is added, sulfur is introduced and will combine with the metal ions to form sulfide compounds, which will precipitate in reference to their Ksp values. Some sulfides precipitate and others will remain in solution. As the hydroxide is added, the hydroxide compounds will drop in accordance with the Ksp values as well. This also relies on a weak basic solution. As the solution becomes more sulfuric from the additional hydrogen sulfide gas being applied, the remaining sulfides are precipitated. Although the solution contains a slight excess of ammonium, the addition of carbonate in the form of ammonium carbonate will cause the rest of the non-alkaline metals to precipitate as carbonates. The other metals will remain in solution as ions in accordance to the solubility rules. I'm going to try and explain some of the reactions that occur in the group separation schema, starting with the silver group. When the atoms combine to form a product, the number of reactants must equal the amount in the product. If we had 10 atoms of silver reacting with 10 atoms of chlorine, the product would be a silver chloride compound in a solution. This would be a forward reaction. There will also be a reverse reaction as the atoms would continuously combine and dissociate in the solution. This is known as equilibrium. And the reaction is shown as a silver ion in aqueous phase plus a chlorine ion in aqueous phase, giving us a sodium chloride compound in an aqueous phase. However, if we added more atoms of chlorine to the solution to overcome the equilibrium, all the silver atoms would be consumed in the forward reaction, and the excess chlorine would make a chloride solution. Silver chloride is not soluble in a chloride solution and will precipitate. In this case, the chlorine atoms in solution would be referred to as the common ion. The reaction equation would be altered slightly to show the precipitation of the silver chloride compound as silver ions in the aqueous phase combining with the chlorine ions in the aqueous phase to become a silver chloride solid, that is, a precipitate. Note the arrow change in the equations. Also note the change from aqueous to solid with the down arrow signifying the precipitation of the silver chloride. Also note that a large excess of chlorine due to an excess of HCl being added can and will result in a soluble complex of silver dichloride. That is why diluted hydrochloric acid is used sparingly. I would like you to locate and download a free copy of the solubility product constant table of the compounds, which should look like the one on this slide. It lists the KSP values for most of the commonly known compounds. It represents the equilibrium concept that I briefly discussed. The equation should look like this: KSP equals M times X. When the atoms of M and X are equal, the value of KSP represents the product at equilibrium. It is a little more complicated and will be discussed in a future presentation in this series. As mentioned in the previous slides, the KSP value is important in determining if a compound will precipitate or not. The group 4 compounds have higher KSP values and will not precipitate easily. Adding hydrogen sulfide gas to the solution results in some of the gas dissociating in the solution. The equation shows that the gas becomes one atom of hydrogen and a hydrogen sulfide compound, which then further reduces to 2 hydrogen atoms and 1 atom of sulfur. Any copper in solution will combine with a sulfur in solution to form copper sulfide, as shown, where we have a copper atom and a sulfur atom combining to form copper sulfide as a solid, which is a precipitate. Since sulfides are insoluble in a sulfide solution, they will precipitate. Those sulfides that have higher KSP values will stay in solution. That is, if the chloride solution is of the right pH value and of sufficient concentration to keep all remaining elements in solution as ions. After the group 2 elements are precipitated and the solution decanted into the third test tube, most of the chlorine ions would have been depleted. Additional chlorine is added to this now weakened acidic solution by adding ammonium chloride. Consulting the solubility of common compounds and waters table, you will notice that all elements are soluble in a solution containing ammonium ion, as well as chlorine ions. Adding ammonium hydroxide will precipitate the hydroxides. The ammonium hydroxide will dissociate into ammonium ions and hydroxide ions. The hydroxide ion will not be sufficient enough. This is because the ammonium ion is the common ion. The ionization of the ammonium hydroxide will be limited and the hydroxide ion will be reduced. Any compound with a large KSP value will not precipitate and will remain in solution. All elemental compounds in the group 3 group have lower KSP values and therefore will precipitate as hydroxides and oxides as the hydroxide is reduced. After the group 3 elements were separated, there will be some ammonium hydroxide and ammonium chloride left in solution. By passing hydrogen sulfide gas through the filtrate, the sulfur ion increases in concentration and additional water is produced. The ammonium hydroxide dissociates to form water, leaving the sulfur ion free to combine with the elements that will precipitate, leaving all others in solution. This is evident when referring to the solubility of common compounds in water table. Therefore, zinc, for example, will combine with the sulfur atom to form zinc sulfide and will precipitate as a solid. Adding ammonium carbonate to the group 6 solution will precipitate the calcium, etc. as a carbonate. The rest will remain in solution as all the remaining ions are soluble in ammonium. The ammonium carbonate dissociates into ammonium ions and carbonate ions, all as ion in the aqueous phase. Strontium is one of those group 5 elements. It will combine with the carbonate ion as strontium carbonate. Due to the ammonium and chlorine left in solution, all other elements will remain in solution. If the group 6 filtrate was left to evaporate, ammonium salts would be formed. Hence, this group is not evaporated and will be treated later during elemental separation. There will be times that your ore material or concentrates will contain phosphates, borates, fluorides, cyanides, and most often, silicates. Magnesium, calcium, barium, strontium, zinc, manganese, and others could precipitate as phosphates during the group 3 separation. Therefore, phosphates will need to be removed first. Borates and fluorides will need to be removed as the group 4 and 5 elements may precipitate, as they are insoluble compounds when formed. After the separation of the group 2 elements and transferring the filtrate to a beaker, 2 drops of diluted nitric acid is added along with 6 drops of 5% zirconium nitrate. Any precipitate that forms will need to be discarded as zirconium phosphate. You may need to repeat the procedure. To remove the fluorine and boron, do so by multiple evaporation using concentrated hydrochloric acid. The last evaporation is done to a small bulk. Then adding 2 mL of bromine water, boil the solution to a small bulk and add solid ammonium chloride. Transfer that to a test tube and then add 6 molar ammonium hydroxide until it's just alkaline. Then complete the separation of the group 3 compounds. This is important and must be addressed. If you suspect cyanide in your concentrate or ore, the cyanide must be removed prior. In order to destroy the cyanide before the group 1 separation, add concentrated nitric acid to the sample, then evaporate to dryness in a water bath. Cyanide will react with the acid to produce a deadly, toxic cyanide gas, hydrogen cyanide. It also prevents sulfide from precipitating. You need to complete this procedure using a fume hood or outdoors with the wind at your back. Cyanide gas will kill you quickly. You can then add the diluted hydrochloric acid. Heat the sample in a water bath for an hour to bring it back into solution. Hydrogen cyanide is volatile in an acidic solution. The next few slides will be the group separation process in chart form, starting with the sample preparation. Grind or pulverize the sample to -150 to 200 mesh and mix thoroughly, that is to homogenize the sample. Place 0.2 grams into a test tube and wash it with cold distilled water and decant. Discard the filtrate. To the residual, add a few drops of dilute hydrochloric acid and evaporate to dryness. Do not heat as some elements present may be volatile. Continue to the group separation, starting with group 1, the silver group. Now that we covered most of the reactions involved in some of the theory, I hope that I was able to present it in a simple, meaningful way, without a lot of theory which may confuse someone without some basic chemistry. It is time to build a flowchart and present a simple procedure that one can follow for the qualitative separation of the groups. To your dried sample of 0.2 grams that was placed in a clean dry test tube, add a few drops of 6 molar hydrochloric acid until the solution is cloudy. Stir the mixture, then add, dropwise, hydrochloric acid until the solution becomes a little clearer. Centrifuge and decant the solution into a clean test tube. Label the test tube containing the residual as Group 1 and cap it. Set it aside for further processing of the Group 1 elements. Continue on to Group 2 A and B separation. Do not use excessive amount of hydrochloric acid, as this may cause the silver to form a soluble silver dichloride compound, resulting in the loss of any silver present. Dilute the filtrate from the Group 1 separation 5 times with distilled water. Slowly pass the hydrogen sulfide gas through the solution. If a precipitate starts to form, continue passing the gas through the filtrate until precipitation ceases. Centrifuge and decant into a small beaker if phosphates, borates, fluorides, and silicates are suspected. If not, then decant into a new clean test tube. Label the test tube containing the precipitate as Group 2 and set it aside for further processing of the Group 2 elements. If contaminants are suspected, continue to the removal of the phosphates, etc. If contaminants are not suspected, then continue on to the Group 3 separation procedure. For the removal of the phosphates, fluorine and borates, to the filtrate from the Group 2 separation placed into a beaker, add 2 drops of diluted nitric acid, along with 6 drops of 5% zirconium-4 nitrate. Any precipitate that forms will need to be discarded as zirconium phosphate. You may need to repeat the procedure. Decant into another beaker and discard the precipitate. Then, to remove the fluorine and boron, do so by multiple evaporation using concentrated hydrochloric acid in a water bath. The last evaporation is to a small bulk. Then add 2 mL of bromine water, boil the solution to a small bulk once more, and add a small amount of solid ammonium chloride. Transfer to a test tube and add 6 molar ammonium hydroxide until it is just alkaline. Then complete the separation of the Group 3 compounds. From the filtrate from the Group 2 separation, dissolve some ammonium chloride salt and add 6 molar ammonium hydroxide, or from the contaminant removal procedure, add enough aqueous 6 molar ammonium hydroxide until it's just alkaline. Test with litmus paper if pH meter is not available. pH value of the solution should be between 8 and 9. If precipitate forms, centrifuge and decant solution to a clean test tube. The test tube containing the precipitate, cap and label as Group 3 elements, then continue to the Group 4 separation. To the filtrate from the Step 3 separation procedure, pass some hydrogen sulfide gas through the solution for about 30 seconds. If any precipitate forms, centrifuge and decant the filtrate into another clean beaker. Cap and label the precipitate as Group 4 elements and set aside with the rest. Continue on to the Group 5 separation process. Boil the filtrate in the beaker to a small volume. Any precipitate must be separated. Centrifuge and decant the filtrate into a clean test tube. The precipitate collected may be discarded, as it will be unwanted sulfur. To the filtrate, add some ammonium carbonate solution dropwise, and while warming in a water bath, precipitate the carbonates. Centrifuge and decant into a clean test tube. Cap the test tube containing the precipitate and label as Group 5 elements. The test tube containing the filtrate from the Group 5 separation. Just cap it and label as Group 6 elements and set it aside with the others. The Group 6 elements will be further treated during the elemental separation from the groups as they are ions in solution. No precipitates, or there shouldn't be. In addition to, the Group 2 elements will be further separated prior to the elemental separation process. All will be shown in Part 4 of this series. Part 3 of this series introduced you to the process and procedures used for the group separation. The process of qualitative chemical analysis is in the form of 2 sets of procedures. The second set will be explained in Part 4 of this series. I hope that this presentation was not too confusing, albeit maybe a little boring. Like all my presentations, please like, subscribe, and definitely share if you know someone that may benefit from this subject matter. The video presentation is free to download and distribute, but not for profit. There was some mention to tables in this presentation, and if you are unable to locate and download some free copies of the tables, please contact me and I will be happy to send you a PDF copy of the tables. I am Rob Boyko Mineral Exploration, and I hope to see you in Part 4 when the video portion is published.